imagine spending like 6 months and millions of dollars building this massive enterprise software system.
Oh, yeah.
And then the entire architecture just collapses because the developer added a new type of customer.
Right. The system just comes screeching to a halt.
Exactly. The database gets corrupted, and the dev team is just staring at this tangled web of dependencies that they can't untangle.
It's a total nightmare scenario.
It is. And that is exactly what happens when you treat software design like a grocery list.
Yeah, when you just scan a dense requirements document.
And you just pick out the nouns, right? Like customer, account, invoice, shopping cart.
Right, and you just start mindlessly generating classes. It is honestly the most common trap in object-oriented programming.
Because it's the path of least resistance.
Exactly. You see a noun, you create a data structure for it, and you sort of assume the architecture will naturally reveal itself.
Which, spoiler alert, it doesn't.
Yeah, no, it really doesn't. As the source material we are looking at today, Chapter 5, Design of Objects, makes brutally clear that noun hunting approach completely ignores the actual behavioral mechanics of a system.
Right, and that's why we're taking the messy reality of these requirements and discovering that proper object design is really about fabricating highly intelligent software entities that collaborate seamlessly.
Seamlessly being the key word there.
Always. So welcome to this deep dive. Our mission today is decoding this chaotic world of object design.
We really want to help you translate those messy real-world requirements into clean functional code.
Yeah, without creating a monolithic, over-engineered disaster. Okay, let's unpack this, because the core tension here is that software objects don't always map cleanly to physical reality.
No, they don't. Sometimes we have to invent entities that just don't exist in the physical world to make the software function efficiently.
Or, conversely, we give a familiar entity completely alien responsibilities, right?
Yes, I mean, in the real world, an invoice doesn't calculate its own tax rate and then mail itself to a customer.
That would be convenient, but no.
Right. But in software, giving the invoice object those specific responsibilities might be the exact right architectural move. We have to, separate the physical world from the digital model.
Which means before we can even start building these intelligent software entities, we have to figure out the actual work being done.
Yes.
We don't start with the objects, we start with the tasks.
And that is the essence of functional decomposition. You look at the entire proposed system, and rather than asking, what are the things, you ask, what are the actions?
Right.
You break the system down into manageable modules or subtasks. You isolate the distinct operations required to make a feature work.
I always think of this phase kind of like casting a theater play, but like a highly dynamic one where the script is constantly being rewritten.
That's a great way to put it.
Because you wouldn't just grab random actors off the street, put them on stage, and then try to write the dialogue around whatever costumes they happen to be wearing.
I mean, that would certainly be avant-garde.
Very abstract.
But it's a terrible way to build enterprise software.
Totally. You take the script, so the software requirements, and you break it down into individual scenes and specific actions. That's the functional decomposition.
Right.
And once you have that master list of required actions, then you figure out what kinds of actors or, objects you need to perform them.
Yeah, okay.
But let's dig into the mechanics of that. The text uses an online bill payment system as an example.
Right, the bill payment scenario.
So if I'm doing functional decomposition on, say, scheduling a payment, how do I go from a list of actions to a refined object model?
Well, you utilize that scenario to drive an iterative refactoring process. So when you break down the schedule payment use case, you generate a list of unassigned tasks.
Like what?
Like checking the account balance, verifying the routing number, calculating the processing fee, scheduling the database right. Those tasks just sit on a list. As a developer, you pull a task from that list and make a design decision. Do I assign this responsibility to an existing object, or do I need to invent a new domain object to handle it?
And that implies we are constantly validating our choices as that list shrinks.
Yes, exactly.
Because the source text talks about static and dynamic validation here. And static validation is essentially looking at our structural blueprint and checking for redundancies.
Right, like are two different objects trying to calculate the same processing fee.
Exactly. And then dynamic validation is much more conceptual. We mentally, or maybe through prototyping, simulate the runtime environment.
We walk through the call stack.
Right. If the payment scheduler tells the bank account to deduct funds, does the bank account actually have the necessary data to do that? Or does it need to query a third object?
And that simulation is where the object model really takes shape. You uncover all those missing parameters and the hidden dependencies.
Because things always pop up.
Always. And as the system requirements inevitably evolve, that unassigned task list gets updated, which continuously drives this iterative refactoring. The objects just get smarter and more refined with every single pass.
So we have our breakdown, our unassigned task list, and we are iteratively assigning responsibilities to our objects.
Yep.
But this is where the architectural anxiety usually kicks in for me.
Oh, I know where you're going with this.
Right. When you have a massive list of tasks, the temptation is to build a hyper-specific object for every conceivable future scenario.
Yes, the what-if game.
Exactly. And yeah, again, you aren't going to need... It is the standard defense against this.
It's a lifesaver.
I know the principle. We all know we shouldn't write code for hypothetical futures. But, I mean, in massive enterprise systems, ignoring future possibilities often feels kind of reckless.
It feels risky.
Yeah, aren't we just setting ourselves up for a brutal system-wide rewrite when we inevitably do need that feature?
Well, that is the standard defense for over-engineering. But it's actually a fallacy based on a misunderstanding of what makes code adaptable.
How so?
Because YGNI isn't about ignoring the future. It's about preserving agility. When you build objects based on presumptions without reliable information, you aren't future-proofing the system.
What are you doing then?
You are just injecting speculative complexity. Every unnecessary object, every speculative interface, it's a tax on the development team.
Oh, that makes sense.
It has to be tested, it has to be maintained, and crucially, it obscures the actual necessary logic of the system.
I see where you're going. It's about cognitive load for the team.
Exactly.
Like, if I'm a new developer looking at the architecture and 50% of the objects are just sitting there waiting for a future feature that hasn't even been approved yet, I can't tell what the system is actually doing today.
Furthermore, YGNI is a critical tool for killing off trivial objects.
Right, trivial objects.
A trivial object is basically an anemic data container. It holds maybe a string and an integer, and it has getter and setter methods, but no behavioral logic.
It doesn't actually do anything.
Just a passive bucket of data.
But what is the actual architectural harm there? I mean, if it's passive, it's not breaking anything, right?
The harm is in where the computing work actually happens.
Ah, right.
If you have a system full of passive buckets of data, the logic to manipulate that data has to live somewhere.
Oh, right.
So you inevitably end up building these massive, highly centralized control objects manager classes that pull data out of these dumb containers, run the logic, and stuff the data back in.
Which is terrible.
You have essentially recreated procedural programming inside an object-oriented language. You build this monolithic control structure that is incredibly rigid.
Right, so if you change a data field in one of the trivial objects, the centralized manager just breaks.
It completely shatters.
So by using your GUI to ruthlessly purge these trivial data holders, we force the necessary logic down into the remaining objects. We distribute the intelligence.
Exactly.
Here's where it gets really interesting, because that distribution is how we achieve polymorphism. The source text gives a fantastic example using a student object.
Yes. The student model perfectly illustrates the transition from a trivial object to a rich, intelligent one.
Because an anemic student object just holds, what, a name, an ID, and an enrolled status.
Right. But a properly designed student object needs to handle its own complex academic and financial data. And the challenge is that the business rules for a student can vary drastically.
Right. The text points out the trap of designing a method specifically for, like, federal financial aid.
Which is way too narrow.
Yeah. If you hard code a calculate federal aid method into your student object, you are inherently tying the architecture to one specific business context.
Yep.
The minute an international student or a part-time community college student enters the system, students who don't qualify for federal aid but have their own complex assistance programs, the architecture hits a wall.
Because the method signature itself is just too restrictive. So to solve this, we raise the level of abstraction.
Okay, how do we do that?
Instead of specific federal aid, we define a generalized behavioral contract for financial assistance. This is where polymorphism becomes our most powerful tool.
Right.
We can have a community student class and an international student class that both inherit from a base student interface. And they both expose a method called apply for assistance.
But the internal mechanics of that method are completely different for each class.
Exactly. The system doesn't need to know how the student applies for assistance.
Right. A calling object like, say, a billing processor can iterate through a list of thousands of diverse student objects and simply call apply for assistance on each one.
Yes. The runtime environment dynamically resolves which specific block of code to execute based on the actual type of student object currently in memory.
It pushes the responsibility of knowing the rules into the entity that actually cares about the rules.
Exactly.
The billing processor doesn't need a massive, unreadable block of ifalse statements, checking, if student is international, do this, else if student is part-time, do this.
No, it just sends the message and trusts the polymorphic object to handle its own complexity.
That elimination of centralized conditional logic is really the primary benefit of polymorphism, isn't it?
It absolutely is.
Yeah.
It makes the system infinitely extensible. If the university introduces a new corporate-sponsored student category next year, you don't have to touch the billing processor at all.
You just create the new class, implement the interface, and the system inherently knows how to interact with it.
Exactly.
I am fully on board with distributing the intelligence, but, and this raises an important question, if we have all these independent polymorphic objects handling complex, varied behaviors autonomously, how do we guarantee systemic integrity?
Ah, that is the million-dollar question.
Right. Like if the corporate-sponsored student is writing its own rules for financial assistance, how do we ensure it doesn't accidentally violate a core university policy?
Right.
Especially during the design phase, when we are just mapping these interactions out before writing the actual implementation code.
Well, this raises an important question about invariance. We use invariance to keep the code honest. Specifically, representation invariance or class invariance.
Right. Designed by contract.
Yes. As you likely know, an invariant is a contractual guarantee. It is a logical condition that must hold true for an object from the moment it is instantiated until it is destroyed.
Aside from brief private moments during internal state transitions, of course.
Of course.
So if I have a bank account object, the invariant is like the balance cannot be undefined and the currency type must be valid.
Right.
But the text focuses on abstract invariance. If an invariant is a strict contractual rule, how do you define it abstractly? Don't you need to know the specific data structures, like whether the balance is a float or a custom decimal object, to write a meaningful rule?
Not at the architectural level. And that's actually a really common misconception that forces developers to make premature data structure decisions. Yeah, abstract invariants allow us to define the behavioral boundaries of an object entirely conceptually.
Right.
We don't need the precise syntax or variable names yet.
We just need the concepts.
Right, we need to document the absolute truths of the domain model.
Okay, let's apply that to the student object. We know the student has an academic record and a financial status, but at this stage in functional decomposition, we have no idea if the academic record is going to be an array of grades, a linked list of course objects, or just a simple GPA float.
And we shouldn't care yet.
Really?
Really.
Yeah.
The abstract invariant is stated in domain language. For example, a student's academic record must always reflect a state consistent with the school's definition of good academic standing. Or any financial aid applied must be strictly compliant with current regulatory caps.
So we're essentially writing the acceptance criteria for the architecture itself. We're laying down the law saying, whatever data structure you eventually choose for the academic record, it absolutely must be capable of enforcing this regulatory check.
Precisely. Abstract invariants basically bridge the gap between messy real-world requirements and rigid unit tests. They document the intent of the design.
So when a developer later comes in to actually write the corporate-sponsored student class, they look at the abstract invariant and know exactly what boundary conditions their code must enforce.
Yes, and it prevents logic bugs from creeping in during implementation because the behavioral responsibilities were locked down during design.
Okay, so we have used functional decomposition to uncover our tasks.
Yep.
We've utilized Way, G, and I to prevent the rise of monolithic manager classes. We've leveraged polymorphism to create rich, autonomous objects that handle their own business logic.
It's a solid foundation.
And we've bound them with abstract invariants so they don't go rogue.
Right.
So we have built highly intelligent, highly reliable software entities. But software isn't just about independent objects, it's about how they interact.
It is social ecosystem.
Right. So how do we design the communication between these objects without creating a chaotic, tangled mess?
The health of an object-oriented system ultimately comes down to two forces, cohesion and coupling. They dictate the social etiquette for objects.
Cohesion being the internal focus of the object, and coupling being its external dependencies.
Yes. High cohesion means an object is doing one specific job and doing it incredibly well. All of its internal data and methods are intimately related to that single responsibility.
And low coupling.
Low coupling means the object relies on as few external classes as possible to get its job done.
When objects are too tightly coupled, it always reminds me of like a micromanager boss.
Oh, that is a perfect analogy.
Right. A terrible, highly coupled manager doesn't just ask for the result of your work. They demand access to your raw data, your personal scratch pad, your login credentials, and then they attempt to do your job for you at their desk.
Which is maddening.
It's incredibly inefficient, and the moment you change how you format your internal data, the manager's entire process breaks.
Exactly.
Whereas a loosely coupled boss just says, send me the final quarterly report. They don't care how you generated it.
That is a perfect encapsulation of the law of Demeter, which the text highlights as a critical design principle. It's also known as the principle of least knowledge, or, more practically, tell, don't ask.
Tell, don't ask. I've always liked that phrasing, but in practice, doesn't that risk bloating the receiving object?
What do you mean?
Well, if the manager is always telling the object to do the work instead of asking for the data to do it themselves, doesn't the object end up with 100 different methods for every possible managerial request?
That's where high cohesion acts as the counterbalance. You don't push unrelated logic into the object. You only push logic that fundamentally belongs to the object's core responsibility.
Okay, that makes sense.
The text actually uses an order manager and an order object to illustrate this. A tightly coupled design would have the order manager call a getItems method on the order, pull the raw array of products out, iterate through them, check the prices, and calculate the total sales value itself.
The micromanager boss digging through the filing cabinet.
Yes. And it ruins the cohesion of the order object because the order is no longer managing its own internal state. It's just a dumb data bucket again.
Right.
Furthermore, if you change the internal data structure of the order, say moving from a standard array to a custom line item collection, the order manager's calculation loop crashes.
So the solution is tell, don't ask.
Exactly. The order manager should never ask for the raw items. It should simply call getOrderValue on the order object. It tells the order to do its own math and return the result.
Send me the final quarterly report.
Exactly.
The manager is entirely insulated from how the order actually structures its internal data. But let's scale this up. We're talking about direct object-to-object interaction. But what happens when this tight coupling infects an inheritance hierarchy?
Oh boy.
Because that is where systems truly go to die.
If we connect this to the bigger picture, you are referring to the fragile base class problem, which is arguably the most destructive consequence of tight coupling.
Let's break that down for the listener because it's a terrifying concept when you experience it in the wild.
It really is.
You have a parent class, a base class, and dozens of child classes inheriting from it.
Right. Imagine a base transaction class in a massive financial system. It handles basic routing logic. You have a deeply nested subclass, maybe an international currency transaction, that overrides some of the parent's methods, but implicitly relies on the parent handling the database connection in a very specific, undocumented way.
So they are tightly coupled through inheritance.
Yes.
And then a completely unrelated team needs to add like an audit logging feature. So they go to the base transaction class, they add a few lines of code to the database connection method to write to a log file, and they push it to production.
They think they just added a harmless feature to the parent.
But because that international currency transaction subclass was tightly coupled to the internal implicit behavior of the parent, that minor change in the base class alters the state execution order just enough to break the subclass.
Suddenly, international payments are failing system-wide.
It's chaos.
A change at the top of the hierarchy triggered a disastrous, unpredictable chain reaction of bugs all the way down. The base class has become completely fragile. You are terrified to touch it.
That paralysis is the death of agile software. So how does the design philosophy in this chapter prevent the fragile base class problem?
By enforcing behavioral orthogonality.
Orthogonality, meaning the behaviors intersect at right angles. They're completely independent and non-overlapping.
Exactly. It is a strict application of the DRY principle, don't repeat yourself, but apply to object behavior, not just code lines.
Ah, I see.
If a base class and a subclass have overlapping responsibilities, or if two sibling objects can both manipulate the same piece of systemic state, you lose orthogonality.
They are competing.
Right. A robust system requires objects to be distinct, non-overlapping experts. The base class provides a rigid, abstract framework, and the subclasses implement specific, isolated behaviors without relying on the internal implementation details of the parent.
So what does this all mean for us as we close out this deep dive? We started with a warning against the naive approach of noun hunting in a requirements document.
We did.
We saw that functional decomposition is the engine of design, driving an iterative refactoring process where we map out tasks and dynamically validate object interactions.
Yep.
We use Yaya GNI not just to save time, but to actively prevent the creation of anemic data structures and monolithic manager classes.
It keeps the system clean.
And we embrace polymorphism to distribute intelligence, letting autonomous objects like our student handle complex, varied rules without cluttering the system with conditional logic.
Absolutely.
We enforce the integrity of those objects early in the design phase using abstract invariance. And finally, we protect the entire ecosystem using the law of Demeter and orthogonal design, ensuring our highly cohesive objects communicate without triggering the fragile base class problem.
It is an incredibly delicate balancing act. But when you apply these principles rigorously, you stop fighting the architecture.
Right.
The system stops being a brittle, tangled web and becomes a flexible, resilient model that can easily absorb new requirements.
I want to leave you with a thought-provoking idea to explore on your own. We have spent this entire time deep in the weeds of software architecture, but take a look at the human systems operating around you today.
Oh, that's an interesting shift.
Right. Look at the workflow in a busy hospital or a corporate finance department or even a commercial kitchen. Are the people in those systems operating as highly cohesive experts with low coupling?
Or are they just micromanaging each other?
Exactly. Are they tangled in a web of micromanagement, constantly reaching into each other's domain, violating the human equivalent of the law of Demeter?
That is a great way to think about it.
Think about how applying these very specific software design principles, giving people clear orthogonal responsibilities, establishing abstract invariants for their behavioral boundaries, and communicating by telling rather than asking could actually be the secret to optimizing messy, real-world human workflows.
It really put things in perspective.
Sometimes the best way to untangle human chaos is to think exactly like a software architect.